So hello everyone, this is Xen API Archaeology, creating a full-featured VMI debugger for the Xen Hypervisor. I am Spencer Michaels. So very briefly, I am a security consultant at NCC Group, where aside from my usual fare of application and network security testing, I do a lot of my own self-directed research in between projects. And recently that has taken me to looking at unikernels, largely because I'm interested in sort of low-level operating system kernel-related things, and unikernels haven't really gotten a lot of security research recently. In the process of looking at unikernels, primarily I was looking at unikernels on Xen, and in the process I developed Xendbg, which is, as far as I know, the first publicly available full-featured Xen VMI debugger using the modern Xen VMI APIs. My unikernel research has been going on for about 2 years now, since I started interning at NCC in 2017. And because most unikernels are either primarily or exclusively designed for Xen, at least when I was looking at them starting in about 2017, I ended up through a rather long and arduous process at this conference. Now, my research was focused primarily on low-level security, things like how stack and heap overflows are prevented, how entropy is set up, or ELF sections are initialized, those kinds of things. And often that sort of information is difficult to get out of just a regular test program running on the unikernel, right? You can't just write like test.c and figure out like how entropy is initialized. And for that you need some sort of debugging capability to look at the actual early startup. Or you're doing something like exploit development with memory corruption, where by definition those kinds of exploits jump out of the context of whatever program has crashed and do something unpredictable. So it's very hard to get useful output out of a program that you've written. So for all that, you need some sort of debugging capability. And you might be wondering, okay, well, why did I go to the trouble of writing my own debugger and then presenting it at a conference? Like, couldn't I just debug the normal way? Well, it turns out that on unikernels you cannot debug the normal way, because basically the way that you would debug on, say, Linux or something like that is to run a debugger as a separate process and then attach it to some simple test program that does something interesting for you, like crashes, and then sort of step and see what happens. But the problem is unikernels, architecturally, their main selling point is that you can only run one process on them. In fact, in a sense, there aren't actually processes. It's just one program that's baked in at compile time and it runs directly in kernel space. And by the way, all the security problems that are involved with doing something like that can be found in my previous white paper and talk. It's pretty fun. But there are a couple of alternatives to that debugging model that you would find, say, on like a regular Linux distro. One way you could do it is use a built-in debug shell or a debug bridge. One example of that on Linux would be KDB. And here basically you have a debugger embedded in the kernel that you either have an interface to from the kernel or you connect to externally through some port it exposes. But this has a bunch of potential drawbacks. Firstly, especially in a unikernel where there's no user space and the application is actually running in kernel space, it's the same memory space. You're going to have the kernel debugger and the application running in the same space, and potentially the debugger could do something that, it could damage the application in a way that also damages the underlying substrate that the debugger is sitting on. And so the debugger could do something to make itself unstable, and that limits the operations potentially that the debugger can do. You also have the problem that obviously the kernel debugger, being part of the kernel, requires the kernel to have been at least bootstrapped to some extent beforehand. So very early initialization, which is something I had to look at, literally the first tens of instructions were relevant to what I was doing. You just can't look at those with a kernel debugger. The way that a kernel debugger works is to basically constantly trap from the code that would typically be running back into the debugger code in order to update the debugger state, and it pretty much has to block for all user inputs. So you get a very, very large performance hit compared to running without a debugger. And even if none of that bothers you, you still have to contend with the fact that a kernel debugger would have to be implemented specifically as a part of the kernel you want to debug. It's not something you can impose from the outside, and as far as I know, there aren't any unikernels that implement this. At least not the ones I looked at. So the other alternative is to debug the unikernel from the outside using virtual machine introspection, which I think pretty much everyone at this conference will know what that is, but for the benefit of those watching this on YouTube later, VMI basically means using the capabilities of the hypervisor, which obviously include arbitrarily reading and writing the contents of the VMs that it's managing, to perform debugging operations on those VMs. And compared to something like a kernel debugger on the VM, this has a lot of advantages. You are running a level below the target. The hypervisor is external to the VM, and at least assuming that it is a secure hypervisor, anything that happens inside the VM can't affect the state of the hypervisor. So you can do whatever you want to the VM without having to worry about it breaking your debugger. And because the debugger state is external to the VM. It doesn't matter if the VM is initialized or not. You can still debug it just as well. So you can literally debug from exactly the first instruction, and it works the same way as debugging at any other state. While there is still a performance hit, there is a much lesser degradation than something like kernel debugging, because generally speaking, you can let the guest run normally, but when it hits an interesting event, you basically pause it and do some debugging operations. In addition, certain operations you can do on the guest are non-blocking. Importantly, hypervisor debugging will work for any VM regardless of the actual contents of the VM, in other words, what operating system is running on it, because to a hypervisor, a VM is essentially just a state machine with a collection of instructions that it's running. It doesn't really matter what higher level operation, or higher level like operating system or other abstraction that makes up, because that's essentially sort of irrelevant to the hypervisor at that level, so you can just debug everything in the same way. Although with hypervisor debugging, you may get less granular information than you would with a debugger running on the target OS or other thing, because basically you don't get the granularity of like using the operating system APIs to get process information and such, although you can extract that manually, actually. Now, many of you will know that GDB does, Xen comes with a GDB debug bridge called GDBSX, which serves as a very basic debugger. Basic is a nice term for it. It's not pleasant to use. It was written, according to a blog post I found, about 12 years ago, and that was way, way, way before any of the current VMI APIs existed. I think at that time there were no VMI APIs, because if you look at the GDBSX code, the way that it does almost all guest operations is to use these hypercalls that all have the word GDBSX in them, which makes me think that they were implemented explicitly for GDBSX to be able to do debugging operations, because at the time there was no alternative. Oh dear. Well, apparently there were two. It is missing a great deal of basic functionality, including breakpoints. Actually, this is kind of weird. There's dead code to check for breakpoints in it, but it just doesn't implement the part of the GDB remote protocol that would let you like insert it via GDB. So if you can get it to work, it's basically just a peek poke debugger. It can read and write memory and maybe registers depending on your version of GDBSX and GDB, because it doesn't quite speak the remote protocol correctly and it can't exchange registers with GDB in all cases. There are actually no generic alternatives to GDBSX, at least there weren't before I developed Xendbg. And I do have to qualify this with generic, though, because there is actually a library called libvmi, which basically is like a cross-platform VMI library for Xen and KVM and maybe other hypervisors, I don't recall. But it only supports Windows and Linux VMs. So while you could build a debugger on top of it, it wouldn't support unikernels, which was what I needed. So you might be wondering, given the gap that is left by the rather lack of functionality of GDBSX, why isn't there a better alternative? Well, after making a debugger, I'm pretty sure that the reason is documentation, because the Xen VMI APIs are, and I mean this very literally, almost completely undocumented. For the most part, APIs for even very basic debugging functions are not mentioned anywhere usefully discoverable online. If you Google search something like Xen VMI single step or Xen VMI breakpoints, you're not going to find anything related to how you actually enable single step mode or check for breakpoints getting hit, things like that. And even if you grep in the code base, because apparently the function names for these VMI functions changed frequently in the past, the function names for a given operation don't always use the sorts of keywords you'd expect to be used to refer to that operation, so it's even very hard to find them just by like grepping through the code. There's also very little example code. You're not going to find much on the public internet because no one knows how to use these, so no one is actually writing the code. You will find some stuff in libvmi, as well as Xen itself, of course, but a lot of the libvmi code is just copied verbatim from Xen, or just a slight modification of it, and a lot of the Xen example code, like xenaccess.c, uses these API functions in only special cases. So for instance, I think xenaccess.c uses Xen foreign memory map to map guest memory, but it does so in a way where it maps all of guest memory, which is just a special case of the argument. So the general case of mapping a subsection of guest memory is left for the reader to figure out, and there's no other call to that function in anywhere else in Xen. There are also relatively few code comments. You will find header comments, but the actual implementations are almost always uncommented. So I think that nowadays we have so few people using these APIs because there are very few people who know how to use them. And I think to some extent there are probably a lot of people who simply don't know that they exist because they're so difficult to actually discover. So I'm going to fix that in this talk. in which I'm going to detail all of the APIs that you need to write a basic Xen VMI tool. And basically that means one that can do all the typical operations you'd expect of any debugger on any system. I'm going to talk about peek and poke, which is GDBSX feature parity, and that includes memory and register I/O. And then things get a little complicated because, as we all know, Xen has multiple types of guest, arguably 3 now that you have PVH, but the main ones are HVM and PV. And basically, HVM is sort of a lower level abstraction that relies on a lot of pass-through instructions directly to the hardware and CPU level virtualization features, whereas PV is a higher level software, more software abstraction that does a lot of low-level operations via hypercalls to the hypervisor, which are sort of analogous to syscalls to the kernel. So the main takeaway for debugging from this difference is that the HVM and PV VMI APIs, not only because they were developed at vastly different times, HVM came much later, but because the internal implementations of these are quite different, the functionality that's available, as well as just the APIs themselves, are totally divergent for everything beyond peek and poke. The PV VMI APIs are really awful. I think they might just have been implemented so that GDBSX can work and never touched again for the most part. And then HVM VMI is fortunately quite good, and it's also, the way that it's written is also open to future extensibility potentially. I will talk about that quite a bit later. And then if we have time, I'm not sure, I'm also going to talk a little bit about how to use XenStore to get metadata about a domain so that like you can show the name of the domain that you're debugging, and you can monitor domains coming up and down, which I use in Xendbg to open a new port for every domain that comes up. I'm going to make 2 assumptions in my sample code here. The first is that the guests are x86-64 or x86. Obviously, there are other architectures. I was primarily concerned with this, but I just didn't test anything else. I do note that there are some ARM-related things in the debugging API, so it's possible that at least the HVM VMI stuff works on ARM. But I'm not sure because I haven't tested. I have also omitted most error checking code because that would just make the text on my slides too small. So just make sure basically all of these functions are going to return an int, and you should use the standard like error, C error conventions and actually check this in your production code. Okay, so the Xen VMI API is composed of a variety of sub-libraries, and each of these is just sort of a rough categorization of some sort of debugging functionality. You don't need to memorize all of these, but it's good to have a list because in any full-fledged VMI API tool, you're probably going to include almost all of these, but generally speaking, in order to find functions in them, you're just going to have to grep through the code, so this is a good guide to just like where you need to start looking for a given piece of functionality. One thing worth noting about libraries, though, is that they all have a handle associated with them, and you need the handle to use the library, so the handle is always going to be of type library name _ handle, which you open with, you get a pointer to such a handle via library name _ open with args that will differ based on the exact library. Once you have that handle pointer, you pass it as the first argument to every function in that library. And then once you're done using the library, generally speaking, at program close, you run library name _ close and pass it the handle, and that will release the handle. Okay, so knowing that, we can talk about memory I/O, which is the easiest, I would say, of all the VMI API operations, because you don't have to really think about whether or not your guest is PV. This is the only sort of PV HVM agnostic part of the VMI API that I know of. If you look at how GDBSX does memory I/O, it uses the GDBSX specific DOM control hypercall called Xen DOM control GDBSX guest memIO, and this will actually work in modern Xen, but I don't recommend you use it. There are better alternatives. Firstly, I think it's about 12 years old. Given its association with GDBSX. Who knows how long it will be supported for, or if it has weird behavior on stuff that was implemented afterwards. But also it's not very performant in the first place, because the way that it works is it copies a block of guest memory into a buffer in DOM0 and vice versa. So I think you probably will end up copying at least a page each time. So if you're writing and reading back and forth, you're going to end up doing a bunch of copies back and forth that you don't need to do. Because the correct way to do this nowadays is to use Xen foreign memory map from the Xen foreign memory library. And what this will do is create a shared mapping of the guest memory in DOM0. So basically DOM0 has an additional mapping of the same physical memory, and you don't have to copy back and forth. So I'm just going to go through the arguments of this function one by one, because I think it will help to elucidate not only this function itself, which is kind of complicated, but the general structure of arguments in the Xen VMI APIs. Here we see the library handle always being the first argument. DOM is a common argument you'll see in a lot of functions that target one specific domain. It's the unique numeric identifier of the target domain, and you might see it as domain ID or DOM ID in other functions, generally speaking as the second argument of any function that targets an individual domain to perform an operation on it. A lot of Xen tools get this on the command line. You can also get it from XenStore. Prot flags are basically the same as anything on POSIX, like the same you'd pass to mmap, or prot read, prot write, prot exec, and so on. Num pages is obviously the number of pages you want to map, but it is worth noting, especially in a debugger stub, you are going to be mapping pages in terms of how many, or you're going to be mapping memory in terms of how many bytes you want to map, not how many pages. So in order to calculate how many pages you need to store a certain amount of bytes, you can use these constants xc page size and xc page shift in this formula, and that will figure it out for you. Pages is the complicated argument here. It is an array of Xen PFNTs, which are basically just unsigned int, so it's like an index. And these are guest frame numbers, which are indices of the pages on the guest. Those are distinct from guest virtual addresses, which are the addresses you would expect to see in like a debugger UI or in messages that you would send and receive in a debugger stub. And you have to get those GFNs from the GVAs using the function xctranslate foreign address. Note that if you actually dissect functions like Xen foreign memory map, you will find things like, hey, why are the GFNs referred to as MFNs by all the variables? Well, it turns out that oftentimes functions like these were implemented at a time when certain equivalencies between different types of frame numbers held, and in modern Xen they don't, or they don't always. So just be careful if you see references to certain types of frame numbers in the implementations of functions, because they might not always be correct. This is even true for some of the the parameter names of certain API functions. And then the errors array is just, it's the same length as pages, and it basically just, each slot in it corresponds to the error node for mounting mapping a particular page in that pages array. If it's non-zero, then that particular page failed to map. And then xctranslate foreign address, as I said, it translates gets virtual addresses to guest frame numbers. And basically, the first two arguments we know, it's the Xen control handle and the DOM ID, and then you pass it in addition, a virtual CPU ID, which is just a zero-indexed identifier for whatever vCPU you want to target. And then you pass it a virtual address, and it will give you the GFN of the page on which that virtual address resides. If you want to read raw page table entries, by the way, this is the function to look at the implementation for. Unfortunately, there is no Xen VMI function for reading raw page table entries, but basically this function does that, but then it clears out all the other page table entry info except the address that it pulls out of the page table. So just look at the code here for that. And here's a function called map memory, which is basically just a wrapper around Xen foreign memory that I made to illustrate how to use Xen foreign memory map, assuming you were thinking in the sort of idiom of, like, let's say if you were using a debugger stub. So we see it takes the Xen foreign memory and Xen control library handles, and then a domain ID, a virtual CPU, the guest virtual address, the number of bytes you want to map, and then the page protections, which again are the sorts of things that you would know in a debugger stub. Then we calculate the number of pages that we need to store the number of bytes we want to map, using that formula I mentioned earlier. We allocate the pages and errors arrays, both of which are sized num pages. And then we calculate the base guest frame number using xctranslate foreign address and passing it the virtual address that we were given. And here we're assuming that the virtual address is aligned to a page boundary. If it's not, you can always do a little pointer manipulation to adjust for that. And we're going to set the pages array so that basically the first element is base GFN, and then every successive element increments by 1. So you're mapping a continuous series of pages starting at base GFN. Now what's interesting is you don't actually have to do this. You can, I think, map any series of GFNs. They can be discontiguous or out of order, and I think this will still let you map it. So I don't know why practically you'd want to do that, but it's cool that it lets you. Then you call Xen foreign memory map using all those arguments in the order that I explained a moment ago, and it will give you a pointer to a block of memory, which is now mapped into DOM0. Before you start using it, you should check the errors array and make sure there are no non-zero components, which will mean that a page failed to map and potentially the memory is in some sort of undefined state or it's null. Yeah.
This assumes that if you have virtual addresses longer than a page, that all the virtual addresses, that there's a one-to-one, that the physical addresses and the virtual addresses line up?
Yeah, so on unikernels, this was always the case, right. But yeah, you will have to, this is just a simple example, like if you have a more complicated page layout where the GFNs point, like two successive GFNs point to non-contiguous like
Then you have to do the
addresses,
XC
then-
translate for an address inside the loop instead of at the
Yeah.
beginning. Right. Okay.
So yeah, this is the most simple possible example. And then once you are done with the memory, just like mmap and munmap, you have to unmap the memory that you have mapped into DOM0. And basically this function takes, aside from the library handle, the base address of the shared memory, which is the pointer that was returned from Xen memory map, and then the number of pages that you mapped originally, which was one of the arguments you passed into Xen memory map. And that's it for reading memory. That's relatively straightforward as long as you have that wrapper function. Now we're going to talk about register I/O, which is conceptually similar on PV and HVM, but the actual function calls you have to make are different. So for PV, you basically use the functions xcvCPU get context and set context, and these both deal in a context object called vCPU guest context net, which is a union of three structs. I believe that C struct is just for internal usage as far as I can tell. So the ones you need to care about are x64 and x32, and that's basically the 64 and 32-bit register structs. Xen will populate one of those internally based on what it knows about the bitness of the guest. If you want to know which of those to read, you have to know the bitness as well, in which case you can get it via the function xcdomain get guest width, and that will give you the guest width, although note it will be in bytes, not bits, so you're looking for 8 and 4, not 64 and 32. So here's an example of reading and writing registers. We declare a register context struct, and then read the current VM context into it using xcvCPU get context. We, based on the guest width, which we get with xcdomain get guest width, we modify either the 64 or 32-bit instruction pointer, and then we write the now modified context back into the VM so that the instruction pointer is now pointing to dead beef. Okay. HVM register I/O is actually quite similar if you don't care about writing. For that, the easiest way to do it is using the function xcdomain HVM get context partial. And you can actually get multiple aspects of the VM context more than just the registers. So this function, the arguments are a little bit generic. Basically, the register struct is, this is sort of a macro that ends up evaluating to a type, HVM save type CPU, and this is just a register struct. And you pass that to the function xcdomain HVM get context partial. The first two arguments we know, they're the library handle and the domain ID. And then we have to give it a type code, which is just a numeric code that specifies the type of context we want to retrieve. Get context partial just retrieves one context element only. And the type code for retrieving CPU register state, we just use the static value HVM save code CPU. The instance value in this context should just be considered a vCPU IV. I think it may mean other things with different type codes. Yeah. The context buffer argument is just a pointer to that register struct of type HVM save type CPU, and the size is the size of that struct. So you just call that, and it populates the register struct just as the PV get context function I mentioned does. If you want to read and write, though, unfortunately there is no equivalent set context partial. So if you want to set the context back, you need to know the general form of get context and set context, which actually deals in a sort of weird format where it's a series of context objects, essentially, where each piece of context is of known size, but the total number of context objects you can get in that buffer is unknown. So at compile time, you can't know the size of the buffer you'll need to get from HVM domain, or xcdomain HVM get context. And basically, each of those blocks of context data in the buffer is going to be prefixed with a header called an HVM save descriptor, with the type code, which we just saw, that's just identifying the type of data, an instance, which in this case we should think of as vCPU ID, and then length, which is equivalent to like HTTP body length. It's just the number of bytes following the header. So for instance, an update to the CPU context would look like this. This is not a struct that Xen itself defines, but that I just defined here as an example. We have a save descriptor, this basically would have a type code of HVM save code header, which would say, okay, here's the header data, and followed by the actual header data, which is sort of a meta header that says, here's the start of the context packet, followed by register data, and then followed by an end descriptor, which says, here's the end of the packet. Now, I mentioned that you can't know the size of the buffer get context needs at compile time, so the way that you use it is actually like snprintf. You basically call it the first time with the last two arguments, the buffer and the size, being 0, and that will cause it to return the size, the minimum size of the buffer that it would have needed to write to, and you use that to allocate a new buffer, and then use get context again to write to that buffer that you've just allocated, and that will write the buffer, the context to the buffer. Then you need to step over each descriptor in the buffer one by one until you find one with a type code of HVM save code CPU, meaning that the body data is referring to CPU data, CPU register state, and you pass the body of that, or you cast the body of that to type HVM save type CPU pointer, and then there's your CPU data that you can modify the registers however you want. And then you pass the results back to HVM set context. So there's a little bit more boilerplate here, but basically it's the same sort of idea. Okay, we are now at GDBSX feature parity with modern VMI API features, so that's good. Now for something less good, which is the PV VMI API. It is very hacky. Basically, the way that it works is it has a so-called debugging mode, and what this does is it just sort of manipulates the guest behavior a little bit so that it's amenable to debugging enough. Mainly what it does is it makes the guest pause instead of just outright crashing when it hits an int3 instruction, or it gets like a single step int3 trap. And that's the x86 trap to debugger instruction. And basically, you should just enable this mode immediately when you attach to the PV guest, because otherwise you risk crashing it. The way that you do that is using the function xc-domain set debugging, and you pass it an enable flag of 1, or 0 if you want it disabled. So to enable single-step mode on PV, there is not an API call for it as far as I know. The way that you do it is you just set the monitor trap flag, which is OX1000, in the flags register, so R flags or E flags, depending on what the bitness of the vCPU is, or sorry, the bitness of the guest is. And basically you just set that flag on the vCPU that you want to enable single-step mode for, and it will cause the vCPU to trap on every instruction, which in debug mode means it will pause on every instruction. Breakpoints, you don't actually need any extra VMI API calls for this. You just use that memory writing technique I mentioned to write an OXCC, which is the x86 int3 instruction, over over some instruction you want to break at, and then when it hits it, it will pause if you're in debug mode. Note that PV guests implement this slightly incorrectly, where when it hits a breakpoint, it will execute the breakpoint, increment the instruction pointer, and then pause. So if I make a breakpoint at like OX1000, then when that breakpoint is hit and the guest pauses, the instruction pointer will be pointing to OX1001. So after you get a breakpoint, you should just subtract 1 from the instruction pointer to make sure that you don't accidentally resume in the middle of an instruction and cause all sorts of terrible things to happen. Oh, really? Because HVM doesn't do that, so I figured. Oh, huh, okay. I always assumed PV was implementing it wrong and HVM was doing it right, but okay, that's interesting. So the two operations that I mentioned, single step and breakpoints, will both cause the vCPU that hit that event to pause. Unfortunately, there's no way to just get notified that that happened. You have to just constantly brute force poll the guest, say, are you paused, are you paused, are you paused? And the way that you do that is using the raw hypercall Xendbg control GDBSX DOM status. I'm not going to really talk about issuing hypercalls because there are a lot of examples of that in the Xen code base, but basically you declare the hypercall buffer, you fill it with the data you need and issue the hypercall, and then the data that you get back, you're looking for GDBSX DOM status.paused, which will be 1 if the guest was paused, and then GDBSX DOM status.vCPU ID is the ID of the vCPU that hit the event that triggered the pause. There's no way to distinguish between breakpoints and single steps here. Unfortunately, you just have to keep track in the debugger of like if a pause occurs and the instruction pointer is pointing to an address where you know you previously set a breakpoint, then you sort of assume that's a breakpoint, and vice versa. Unfortunately, that is all you can do in the PV VMI API as far as I know. Again, I think that these were mostly just implemented at the time so that GDBSX had something it could do, but it's not particularly extensible. Now, the HVM VMI API, which is a phrase that is really hard to say and I'm going to definitely screw up later in this lecture, but the HVM VMI API is much better and substantially more extensible. The way that it works is DOM0 maps a shared page with the guest on which there's a ring buffer, and the guest will place event notifications into the ring buffer, and those are called requests in the API, and DOM0 will act those requests with responses, which are actually more than just acts. They could do a lot more. The way you set up the ring buffer from DOM0 is called the function xcmonitor_enable, targeting a specific domain. And basically what this will do is map the shared page. It will not initialize it. I'll show you how to do that in a moment, but it will map the shared page and open one side of an event channel on the remote domain that you are debugging and give you that remote port number through the third argument. And basically, you want to take that remote port number and immediately pass it to Xen event chan bind interdomain, which is going to establish an event channel between the remote debugging target and your DOM0, and will return you a local port number that is associated with your side of the event channel. And you want to keep that port number around and also associate it with the domain ID that you passed to XCMonitor enable just a moment ago, because basically when you get pending events on the event channel, they're going to be batched by the port number, and that will allow you to associate a batch of events with the domain that they're coming from. So here's an example of setting up and using the ring buffer. First, we called XCMonitor enable to set up the ring page, get a pointer to it, and then get the remote port. We pass it to we pass the remote port to Xen event chan bind interdomain, and that will set up the event channel and give us a local port. Then this is the initialization you have to do for the ring page, just these two macros, shared ring init and back ring init, and you initialize a back ring value that will be used for future invocations. Make sure to do this right here in this order verbatim, because otherwise the ring page will not be set up correctly and it will behave weirdly, I'm sure. Then you actually enable the events that you want to listen for, and then you read events from the buffer for however long as you want, either until the guest shuts down or your debugger is shutting down, in which case you should call the function Xen event chan unbind, passing it the local port to close down your end of the event channel, and then call XCMonitor disable, passing it the DOM ID to shut down the monitor for that particular domain and unmap the ring page. Because if you don't do this, then other VMI clients will not be able to enable the monitor. It's only sort of one at a time. So to monitor specific event types, which you have to do explicitly, because by default you don't get any events, first I recommend you call the function XCMonitor get capabilities. What that will do is give you a mask of the various events that the guest supports, pass it the DOM ID and the capabilities mask. And basically, if the capabilities mask contains one of a variety of VM event reason flags, which I'll show you in just a second, for instance, VM event reason software breakpoint, then you can call the corresponding XCMonitor event name, in this case software breakpoint, and pass it a DOM ID and an enable flag of 1 to enable that particular event on that particular domain. So here are all the event reason flags. I have not used all of them personally, and today I'm only going to have time to talk about 3 of them: single step, software breakpoint, and then mem access, which we're going to use to catch memory access violations to do data watch points. So to actually read events from the ring buffer, fortunately you don't have to poll for this. You can do it in a non-blocking way. And the way that you do that is you get a file descriptor associated with the event channel from Xen event chan fd, and you basically select on that file descriptor, and when select returns, don't actually try to read anything for the file descriptor. It's just like a signaling mechanism. It doesn't, as far as I know, provide any useful data. And once select returns, you just call Xen event chan pending, and that will give you a local port number associated with the incoming batch of events, which you can then read in a loop, which I have on the next slide. After you are done with reading events, though, make absolutely sure to call the function Xen event chan unmask, passing it the local port. As I understand it, this will release your end of the event channel so that the guest can proceed with putting more events into the ring buffer. I believe basically the event channel will get sort of stopped up if you don't call this function, and you won't get any more events. Okay. Yeah. So, whoops, I should have highlighted those on the way. That's all right. Okay, so to read events, basically you do it in a loop around this macro ring has unconsumed request, and you pass it a pointer to that back ring value that we set up in the early init code. And basically you get a request off the ring buffer, which is, that's just sort of pointer manipulation and macro boilerplate that I have, I have that on a slide that's coming up. Basically all you need to know is that a request is of the type VM event request T, and the first thing you should do when you get a request is check that the API version of the request, rec.version, is the same as your VM event interface version, because if not, then it means that probably you're going to be reading structs that are formatted differently and you'll be reading gibberish, so you should just abort. Then you can process the event, which generally involves switching on request.reason, which is going to be one of those VM event reason flags, and from that you know what type of event it is, and then you can read request.u. whatever the event name is, and that is a struct associated with the data, a struct associated with the event that contains data specific to that event type. Then you have to craft a response, which is VM event response T. This is actually just a type def for the same type that is VM event request T. And then you You have to set the reason, the version, and the vCPU ID to be the same as the request, as far as I know. And then flags does not have to be the same, but I recommend you always mirror back the VM event flag vCPU pause flag, because if you don't, you risk locking up the guest, and I'll explain why in just a little bit. And you put the response back on the ring buffer, which I have the boilerplate for here. These are copied mostly from some place in Xen, I don't remember where, but with the code cleaned up a bit. The macros in here come from Xen itself, so basically just copy this into your debugger code and you should be fine. The request response struct does bear additional explanation, because there's actually a lot you can do with it, just like aside from figuring out what type of event happened. You can perform some operations via responses, for instance, either shortcuts for existing API functions or some sorts of, shortcuts for existing API functions, or basically there are certain operations like spoofing file descriptor reads that you can only do via responses. So I'm just going to go through this in detail, one member at a time. So version, we know already, that's just the API version of the request. Flags is where it gets interesting. It basically carries metadata about the other data that is contained in the responsive request, and basically some flags, if you send them in the response, they will cause Xen to perform operations on the guest. Here's a list of flags, just some examples. Toggle single step, if sent in a response, will cause Xen to flip the single step state on the guest. Set registers will cause the register state that is stored in the response, which I will show you how to do in a moment, to be set as the new state of the guest. The emulate series of flags is pretty cool. It allows you to do things like if you catch a file descriptor event, which is one of those event reason types that I mentioned, you can catch like a file descriptor read. You can provide fake data to read from it, and I think you can also provide fake instruction data to read from the instruction cache. I haven't used these myself personally, but they sound pretty interesting. Reason we know already, those are just the event reason flags. That indicates what type of event it is. vCPU ID is the ID of the vCPU that triggered the event. Alt P2M index is just used with the alternate P2M flag, which you can read about in the header. I should mention actually that the vmEvent.h header has unusually good documentations for those event flags. So if you want to know how to use them, you can basically just read those header comments there. The use union is basically just a union of structs which contain data referring to the particular event types. For every event reason, there is an event struct containing data about that event. And then the data union is kind of weird. It's a union of unions, so there are 4 possibilities. When you get a request, the request is always going to contain the register data at the time of the event. So data.regs. In our case, x86, is going to contain an abbreviated version of the registers. It's a different struct than that earlier HEM register struct I mentioned. When you send an event back, a response back, you can do one of 4 things. You can not set anything, in which case this doesn't matter. You can set the set registers flag, which will set the register state stored as the new register state of the VM. And you can use the emulate series of flags to emulate either file descriptor reads or an instruction that would otherwise have faulted. I mentioned the VM event flag vCPU paused flag, which basically means that if you get it in a request, it means that the vCPU has been paused in response to some event. So if it's like a fault or a breakpoint or something like that, then generally speaking, you'll get this flag. If you pass it back in the response, Xen will unpause the vCPU for you. And the reason it's important to always mirror it back is because vCPU pausing is actually reference counted. So if you don't mirror the flag back whenever you get it, you risk the possibility of getting that sort of pause counter out of sync and then just getting the guest stuck forever. So I recommend, instead of not sending it back when you want to pause, always send the flag back when you get it, and just issue an additional pause request before you send the response, so that you tick the counter up by 1 more, so it's a predictable amount you know to tick back down later. So there's, I think, no API for pausing a vCPU. You have to use this GDBSX pause vCPU hypercall with a corresponding unpause vCPU as well. And you give it the vCPU ID, and it will just pause the corresponding vCPU. But before you do this, it won't let you do this hypercall. It will just give you an eperm unless you first call xcdomain pause to pause the entire domain. And this is a different layer from pausing vCPUs. Basically, if you call xcdomain pause, that just tells Xen, do not simulate this VM at all, stop the state machine. And that's what happens when you run xl pause. But this is separate from pausing a vCPU. So basically what you can do is pause a domain, pause one vCPU, and then unpause the domain. And then that vCPU will stay stuck, and everything else will run normally. And basically, you can use that to implement the GDB's remote non-stop mode, which is how I do it in Xendbg, where you can just step an individual vCPU while letting everything else run as usual. So everything else, now we basically know how to set up and use the VMI event, HVM VMI event channel. Everything else comes easily. To enable single-step events, you use xcmonitor single-step. You pass that an enable flag of 1 to start listening for VM event reads single-step events, and these will be fired on each instruction once you turn single-step on using the function xcdomain debug control. And basically that seems like it was originally made to do generic debug operations, but right now can only do 2, which is turn single-step on and off using that SOP argument and basically passing it those values at the bottom of the slide here. Software breakpoints, you insert them in the same way as I mentioned in PV. You just write an OXCC over something, and then you listen for them with xcmonitor software breakpoint. Note that it apparently sort of defies the usual way that these are handled, and the instruction pointer will point to the breakpoint when it's paused, not after the breakpoint. Watch points are a little bit complicated. Unfortunately, you don't seem to be able to do generic register watch points, because there's no way to get notified when a register changes, but you can do data watch points, and the way you do that is using mem access events, which are listened for with xcmonitor mem access. And what this will do, it's named a little disingenuously. It actually only fires when a memory access violation happens. So that the way you do data watch points, if you're interested in, say, reads on a particular page, you just make the page non-readable so that that page throws a write access violation when a read access violation when the read is attempted. The way you actually set page permissions is using xcsetMemAccess, and this has 2 interesting arguments: XenMemAccess T access, which basically is just like a series of permissions flags, N, WX, RX, etc., and then first PFN, which is a page frame number of the first page that you want to start setting these permissions on. You just get that from a guest virtual address using xctranslate foreign address. Once you get a memaccess event, you should first check the flags member of that event data struct for memaccess GLA valid. And basically, if that flag is there, that means that the address itself, like the memory pointed to by that address, really exists, but it couldn't be accessed because of some kind of permissions error, in which case .gla contains that virtual address, and then you can check if it's in your watchpoint region. Otherwise, that you have a weirder error where some memory that wasn't actually mapped has been accessed, and you should check .gfn and offset for data about that. To remove the watchpoint, you just set the original permissions back using xcsetMemAccess. One side effect that you might have noticed of this is that the way that the event API works for events involving false, like memory access violations, is that it actually just consumes them and doesn't let the guest handle them. So you run into the problem where if you're monitoring for memory access violations to do watchpoints, you might get a real memory access violation. So in other words, you get a memory access violation and you realize, oh wait, this address is not actually in one of my watchpoint regions. So it must actually be, an actual violation. In which case, you should use the function XenDeviceModel inject event to force the guest to handle that particular trap, which generally speaking just means to crash. And this function, I don't really have time to go over all the arguments, but there are a couple of examples of it in the actual Xen code base. Generally speaking, every event data struct contains data that you need to pass as arguments into this function to inject the trap associated with that event struct, for the most part. I'm pretty sure I don't have time to talk about the extras in detail, but basically XenStore you can use to read domain metadata using the XS directory and XS read functions primarily that will allow you to read it's not an actual file system, but file system-like structure of XenStore. And you basically start a XenStore transaction and pass this transaction handle to those functions. It will allow you to do things like read the name of a domain by reading the corresponding sort of file, quote-unquote, entry, and then end the transaction to sort of commit your changes if you've made any changes. I have an example here. You can look at the slides afterwards because I don't have time to go through the whole thing of listing domain names along with DOM IDs as XList would using XenStore. And then XenStore watches are interesting because they allow you to watch for changes in XenStore. Basically, you can use XS watch to watch a particular XenStore path, and it will, you can get an event that says something in this path changed. You can also use the paths at introduce domain and at release domain to, those are like special path strings that will get fired when a new domain is introduced and an existing domain is destroyed. You check for these events essentially in the same way as with the Xen VMI API. You get this XS file no file descriptor, you select on it, and then you just repeatedly call XS check watch on a while loop until it returns null, and that will give you a char pointer that's a pair of strings that's the path and the token. This does not give you any additional data about what was modified. Unfortunately, you just have to reread the path that you're interested in after you get a notification that it's changed. And with that, I apologize for the very abbreviated last bit, but I congratulate you all because you are one of a probably very small group of people, albeit today I hope substantially expanded, people who can write their own Xen VMI debugger. I think the slides are actually already up on the Xen conference website, but they're also on my website as well if you need to find them somewhere else. And you can get and use Xendbg today at github.com/nccgroup/Xendbg. If you want to use some of the code in your own stuff, feel free to with attribution. It is MIT licensed. Just note that it's in C++, not like my C examples here, but all my examples are derived from that, so it's essentially quite similar. I know we are already right on time, so I will end there. If there are any questions, I guess just find me afterwards or email me. Oh, have we got 5 more minutes?
5 minutes, yeah. So one minor thing, was there a slight, I'll ask Andy maybe because he might know, was there a slight race condition in your loop there? Because if you check to see if there's anything on the ring, and then you unmask the event channel and then go to sleep, then there might be things added to the ring between the time you do the last check and the time you unmask your event channel.
My understanding is that if you don't, when the events get delivered to you, the event channel is locked, and then only when you unmask does the guest place new events into the channel. Is that
No, I don't think
correct?
so. What?
Huh.
So when you say read events, there's reading things off the ring.
Yeah.
And then there's receiving event channels, which is slightly different. So the event channel is just to say, by the way, there's new stuff on the ring, but you can put stuff on the guest can put stuff on the ring at any time. Is that right?
Yes, actually, that's an interesting thought because I've actually not tried this with multiple guests attached at once, and so I'm wondering if let's say you check the value of Xen event chain pending and it's a certain local port, and then you read events, and then while you're doing this, some other guest with a different local port pushes another event onto your ring. I'm not sure if that can happen.
So the one ring per guest is one event channel per ring.
Oh, okay, yeah, that makes sense. Okay.
Right. So maybe we want to offline take a look at that and see if there's a race condition and fix that.
Yeah, but I've only ever used this in a debugger for attaching to one guest at a time, so it's very possible that could occur.
Right. And I guess the guest is paused after these events happen, right?
I'm not sure about every event. I know at least like breakpoints and watch points and single step. Yeah, Xen
Right.
will automatically.
Well, that's the problem then, is that if you check the ring and there's nothing on it, and then at that instant the guest puts something else on the ring and sends an event channel, but it's still blocked.
Yeah.
And then you unmask the event channel and then go to sleep, then you might never notice that there was an event on the ring that the guest hasn't seen. No? Oh, okay. Does some magic for you. Okay.
If you unpause like the number of requests pending, you'll wake up immediately next time you hold.
Okay, good. Right, never mind then.
Okay, sure. And yeah, I mean, just know I'm by no means an expert on Xen. I knew nothing about it until I started trying to develop this debugger. So I'm sure there are some errors in these slides. This is more of a practical guide of like, these are the functions you need to call in order to do this, because there was no guide at all to doing any of this before I
Thank you very much for
myself.
that.
Yeah. I will try to write actual documentation based on these slides at some point. Yeah.
Any other questions?
Right. Okay, thank you.